Good morning. I'm Michael Atzmon. I'm pleased to introduce the next speaker, Professor Jyoti Mazumder, who is the Lurie Professor of Mechanical Engineering, also Professor of Material Science and Engineering. He directs the Center of Laser-Aided Intelligent Manufacturing. Professor Mazumder received his bachelor's degree in metallurgical engineering from Calcutta University, and then his PhD from Imperial College in process metallurgy. So far, he's published close to 400 peer-reviewed papers. He has 20 patents, and about 5 years ago, he was elected to the National Academy of Engineering. Professor Mazumder is the fellow of 3 professional societies. He has won more awards than I can list here. Now, he's pioneered a quantitative approach to laser-assisted material synthesis and is best known for inventing a closed-loop direct metal deposition method, which has led to an explosion of 3D printing, also known as additive manufacturing, of metals. And this is a technology that the economists declared as the third industrial revolution. Now, of course, the mechanical properties of metals are very sensitive to the microstructure, which depends on the thermal history. And recently, Professor Mazumder and his coworkers have invented an in-situ diagnostic method which allows one to determine the microstructure of the solid as it's solidifying from the electromagnetic radiation that's emitted from the plasma during laser processing. And so we'll hear more about it. His talk's title is Laser Engineered Materials for Transportation and Infrastructure.
Thanks for an excellent introduction. What I'll talk is slightly different than what Alan did. It's difficult to follow Alan. My talk will be more nuts and bolts than the vision part of it. And what I will try to do is give you an idea how you can take a well-known material, change the structure, and come up with different properties. Essentially, you can tailor the properties of the material using laser. And since I'm following Alan, I'll give some of the examples where lasers are used even for lightweighting of cars. So just to keep the continuity. Outline, basically I'll have what the laser processing is, what's the modeling and measurement, and application goes from angstrom to meters. So I'll try to give you some of those examples, the length scale we are dealing with laser processing. And at the end, we'll have a sort of how to design the material and how you can certify the material. Because one of the things I got started with 3D printing of metals long time back in 1980s. And it has developed, it's now third industrial revolution, which I take it with a grain of salt, because additive manufacturing had been used by humankind of 5,000 years back. A pyramid was built by layer. So it's not a third industrial revolution. It's an old wine put into new bottle. What hasn't been done is how do you know what's the quality of the material? You can make beautiful shape. Last December, I was in India. One of the oldest engineering school in Pune. The undergraduate students have a club for additive manufacturing. And with a $500 machine, they're making all of the Indian deity called Ganesh, which is half elephant, half human being, with a tremendous amount of details. So making shape is not a challenge anymore. If in a third world country, undergraduate students can make it with a few $100s. What is challenge is how do I know the properties I'm getting, whether it's for welding, whether it's for 3D printing. And laser comes handy for this kind of thing. So this is the outline. And since I'm following Alan, I put some of the example of car. This is actually borrowed from my friends in GM. They put in order to reduce the weight of the car, every gram counts, they have put several items in the Cadillac as a way to reduce the car, and these are all laser-based processes. Okay? Or whether TPO is basically mold is made using the laser and reconfigure it. and some of the welding is done with laser. So a huge number of laser has been applied in the car itself on their own neighbor. And you can see why. If you look at the laser processing, the scale, almost any manufacturing process you can think of, from ablation to heat treatment to cladding to 3D printing, all these can be covered with a laser. Laser is just a tool. Like material scientists use electron microscope, laser is just another tool to fabricate the material. So don't think laser is a panacea. It's basically focused heat source with light, and your imagination is the limit how to use it. Okay? So length scale is a huge, it's 12 order of magnitude. As a first example, you can even make nanocrystalline material using this. Now, one of the techniques we developed was essentially using the laser ablate the material, collect in liquid nitrogen cool plate, and most of the material, even the example I'll be giving is even niobium aluminide, I can make nanocrystalline and maintain the composition. Now, why I'm saying that? Niobium melting point is higher than the boiling point of aluminum. So if I can maintain the stoichiometry and make a nanocrystalline material, that gives me a tool. I can make a nanocrystalline material out of anything. Okay? And Alan just mentioned that he's increasing the strength of the aluminum casting, putting nanocrystalline material. So your choice, your portfolio is increased quite a bit using this technique. Now, am I just saying it? You can see we have made material which is as small as 2 nanometer. One atom is 2.5 angstrom. So we basically, width is about 8 atoms. And the average was of 7 to 8 nanometer size by ablating and collecting it. So that's one of the technique, and you can even make nanocrystalline composite. This is 5 nanometers of aluminum and 18 nanometers of niobium aluminide. Niobium aluminide have only 3 slip planes. It's brittle as hell. But if you make a composite like this, you can roll it like a cigarette paper. So the reason I gave this example to show you the amount of flexibility you have to design the material for whatever need you have. Another area was using a femtosecond or a nanosecond laser. You can essentially, obviously have to shape the beam, and you can make channels. And if you look at your body, jokingly I said God is the laziest person in the world. If you look at your body from head to toe, it follows just one formula. The veins, the major veins is breaking down into 2. Cube of the daughter veins, sum of the cube of the daughter veins is equal to the cube of the mother vein. And it starts from your head to toe. Your lungs, your heart, everything follows the same rule. And one of the projects we had a few years back with medical school is to make an artificial lungs. Okay? And this is only 9. Your heart, lungs has 16 divisions. We made up to 14. And essentially, you can make any kind of shapes you want. And not only for biological application, for automobile and other things, you can also use it for mixing purposes too. This is for your heart. You started with 250 micron, you're down to 125, and we've done it about almost 11 times. You might ask, it's so easy to make, why don't I see the lungs, artificial lungs in the market? Biggest bottleneck is not the manufacturing. Biggest bottleneck is how do you grow an endothelial cell, which works as a lubricant for blood flow, on a metallic body or a polymeric body, and keep it alive for more than 2 weeks. Through Takayama was working on it. He couldn't keep it alive more than 2 weeks, but once he's successful, then you'll see the manufacturing is not a problem, is the growing and sale is a problem. But in the meantime, people can use it to make Whitehead and Harvard come up with this kind of a shape which will create the mixing very quickly, because you can rotate the flow by making a herringbone shape. Again, using a laser, you can create those shapes easily, and I think we don't care to read all this. I'll just go. And you can see using this, if you have plain channel and put two liquids together, they won't mix at all. It will take a long time to mix. But if you put a herringbone shape in the channel, it mixes immediately, and mixing time is very small. You can use it for cytometry, you can use it for pathology, you can use it for mixing fluid in any kind of lubrication in the car, all kinds of different applications. So what is giving you a way to make a complicated shape in a small few hundred micron channel in a few seconds. Okay? But question is, I showed you from nanocrystalline to making it shape, but how do you control it? How do you know it's what you want, you're getting that? So one of the major area of the research I carried on since my PhD thesis, so I'm at it for almost 40 years, telling my age. How do you model the process itself? Okay. So what we have done over the years, we developed a mathematical model which has got three-dimensional fluid flow, heat transfer, liquid vapor interface, and that's one of the things most of the people, avoid in modeling is solid vapor interface, liquid vapor interface. Because if you take a continuum mechanics and just do the model based on continuum equation, liquid vapor interface is never continuum. You have a loss of density, loss of temperature, and if you avoid that, you're putting a lot of error into this. So in physics, they call it Knudsen layer. So we borrowed equations from the physics, put into the model, so we also incorporate the liquid vapor interface discontinuity. And after that, we also have multiple reflection, homogeneous boiling and evaporation, and free surface evolution level. Now, this is another thing which we introduced in the modeling community, and the reason I got quite, the professor in mathematics who was working with me, he did it in a level set method is way you can basically track the free surface, whatever surface you get, instead of assuming a surface, was done by a young professor called Smereka in his PhD thesis. He was in Collegian Mathematics department. At the age of 42, he passed away a few years back. So that was sad, but he's a wonderful man to work with. And once we do that, then you can basically model the process. What is the liquid vapor interface? What is the temperature distribution, even in the pool? You get all the information you need. And later on, I'll show you with this, you can essentially, if you're making a 3D printing, you can get the composition distribution, you can get the temperature distribution, and you can even find out what is the particle distribution in the plasma itself. But while you're doing this, Rachel just put the name as transportation. Not only make car component, recently we just published a paper in Medtrans. We can make inch long, and now we are basically with the, thanks to NIST, we're trying to make a 4-inch long, directly writing a single crystal with any shape you want. And G was initially funding it. So once we make the wall, G said, why don't you make a sort of a shape like this, because most of the turbine will have a hole inside to carry the gas. So we showed that we can, any shape you want, we can make it and keep it single crystal. And to best of my knowledge, we are the only group so far who can grow directly write a single crystal. And as a basically joke with G, they said, oh, you won't be able to do it. I said, give me the most difficult material you have to grow single crystal. So they gave me N5, which is pain in the neck even to grow in a conventional process. And we showed that, yes, we can grow the single crystal. And NIST is now trying to funded us to make it up to 4-inch tall, so that that's the minimum turbine size. And not only that, according to General Electric, each time you put a new material, it costs them $1 billion to certify it. All these properties. It's basically for each single design change is $10 million. It's a huge expense. So we're also developing techniques by which we can tell you whether it's a good material, or ugly, good, bad, and ugly. We can basically tell you during the process within 10 milliseconds. Okay? And the process we use to do that is called direct metal deposition, where we are using lasers, CAD, CAM, the sensors, that's my patent actually, and the powder metal. All together works basically building the 5 different technologies we can build, not only single crystal, also metamaterials. And that was done several years back with John O'Halloran's help. And this is a 3D printing machine we installed in Oak Ridge National Laboratory. I had a startup company based on that. That's another funny story. I used to work with GM to make this, and within a week of joining Michigan, they came to me, build the first machine for us. The year is $2.5 million. University lawyer and GM lawyer fought for 1 year, and I still remember Mitch Goodin's comment to the Chuck Leahy in GM. If Professor Mazumder thinks anything in a bathroom, that belongs to the university. And GM lawyer said, what do I get on $2.5 million? So make the long story short, GM walked out, another group of investors came in, who happens to have the most silky smooth lawyer I've seen. He was governor's lawyer at that time. He got the thing out of the university. And we started making this kind of machine from 1999, and it's installed all over the world. That company sold in 2012. But that's the kind of system. I have Model T in my lab. Using that, I look at the plasma and do all kinds of diagnostics, the height, the composition, all kind of things. Using this, we printed the single crystal, but the company which I founded, they're repairing turbine, making medical components, oil and gas. This is a torque converter for a tank. This is the G90G, G19 engine, titanium cover, valve seat, integrated valve seat. Now, integrated valve seat, that's another funny story. I did that fast, and if you ride a Nissan car, they have integrated valve seats since 1991. Because that's the time they approached me in '89 when we developed the project, did that. GM came after 10 years. Let's do this. And we did the whole instrumented engine, but unfortunately, that was the year 2007. Nobody knows what those engines are now. So GM hasn't implemented, but Japanese, Toyota and Nissan both using this technique to make integrated valve seat, which increases the efficiency by 3%, and engine temperature is gone down by 50 degrees Celsius. Some other application, this is basically, Steve Forrest is not here. We also developed a scaffold using this laser system. Scaffold was designed by Scott Hollister. We made that with the laser, and if you put your BMK7 part of the gene with chloroform in it and salt, within 6 weeks, scaffold is covered with your bone, a bone made out of your own genes. At that time, US Army had 25,000 wounded soldiers. Each soldier was costing them $2 million. So they wanted me to develop the technique and put it in the field. And I can tell you why I can put it in the field. But nobody in this country wanted to try it on human being. USDA rule is from mice, you go to guinea pig to bigger animal like horse, then to gorilla, then you go to the rhesus monkeys, then the human trial. So that's about 25 years. By that time, I'll retire. So I thought, and the universities, I found a Chinese hospital who will test it on human being. But university slapped my wrist because I'm violating USDA rules. So I walked out of any kind of biomedical research that I don't have time left in my life to go through all the tests. This is basically for turbine, and it shows the accuracy. You can make 0.2 millimeter instead of machining. It takes 80% of the material is removed. This is the collapsible part of the turbine blade, turbine engine. You can make it without removing the material, just printing that, and price goes down quite a lot. This is what we did for Rolls-Royce. Another application by laser you can engineer. This is probably I shouldn't say this, but this is for Takata, who have a bad reputation now. But they introduced in their production a mold which we made putting H13 tool steel on copper, which is supposed to be oil and water, shouldn't mix. But we got the extended solid solution, and in 90s, I've got several papers showing how you can do that. And this is the seat belt D-ring by which you can, with the laser help, you can make this. Okay? You can make nanocrystalline material also. That's with titanium, nickel alloys. But the reason I'm saying that I can put it in field, I have a patent where I can put the machine in Ann Arbor and run it in Aachen. Because essentially, the machine which is depositing the material are responding to your digital information. And you can just basically send it by, in fact, Army is trying that. They have a mobile part hospital, and this machine is in now Army's hand. I don't know what they're doing with it. We built the whole machine. It's a $10 million project. We can do the remote manufacturing. We can compress the data. A typical file is about 100 megabytes. Take 30 seconds to go, but you can compress it by 95% without any loss of the data. And data is encrypted 264-bit, because for any defense, the Army, Navy, Air Force, they don't want to send the data in the ether and want someone else to catch it. So 264-bit is the highest encryption you can make, and we have done that and demonstrated this facility. They took the machine, and then I don't know any information, whether they implemented in the field or using it or not. But the point what I'm slowly getting at, that using laser, you can essentially, imagination is your limit. Whether you can remote manufacturing, we can make nanocrystalline material, we can make material with your desired properties. This is one of the examples. We made a CT structure, coefficient, negative coefficient of thermal expansion. Noboru Kikuchi, one of our colleagues then, now he's technical director for Toyota, he designed it, we built it, this is the part, and if you heat this material, instead of expanding, it will shrink. So this is another example that you can essentially design the material based on whatever you need using this technique. So here, what we have done is essentially use the laser to put multiple material. At the same time, put the material following a design and design was based on homogenization design, which will, at the end, tell you how to get whatever property you need. And that basically changes and the whole way society can work. Instead of getting whatever design maker makes, you give it to the research, then he throw it to the design, then you throw it to the customer, whether you like. So basically, design based on the design, whatever the design engineer is thinking, you can totally reverse the process. You can start from back and come up with the structure and the design you want. Okay? But this actually now goes to the additive manufacturing, which becomes a very popular subject. And look at this. In 2012, that's the cover page of Economist, Third Industrial Revolution. I think it's just back to the future. Because if you look at the patent for resins, Chuck Hull's patent, 1986, expired. Joseph Beeman's patent on selective sintering of polymer powder, expired. My patent, it just got cut off. That also expired on metals. So all the major patent on the field is expired. Now it's the third industrial revolution. find it joking. And to put the point, stress it on further, this was a 2,800 BC pyramid made by layer structure. So the concept is known to humankind for 5,000 years. It's just a question of why we haven't used it. But the question what I mentioned right at the beginning, how do I know what product I'm making? You can make product. Kids can do it nowadays. What's the property? And this is the number I got from GE. For cost of design change for turbine blade is $10 million. Cost of certification is $50 million. And total engine is $1 billion. And you cannot apply Teguchi metrics to statistical quality control because number of parts are much smaller. It's not a car industry, you're making 3 million parts and you take every 1,000 parts out and test it destructively. So you have to come up with a way that you know the part non-destructively, quality of it, during the manufacturing process, not after the manufacturing process. And to give you this example, and Alan probably will sympathize with this, this is a measure. Detroit loses $434 million every year for body in white welding. Okay? This galvanized steel welding, the zinc vapor in the middle, it bursts. Zinc boiling point is 900 degrees Celsius, and steel melting point is 1500. So it's a major problem. In order to avoid the crash of the car, if they need 100 oil, they'll make 200. Okay? And companies like Volkswagen, they installed 480 lasers in the last few years for doing laser welding. But still, even with laser welding, you don't know whether you have a porosity or not. And that became, so first one of the solutions, I have a patent on this, is to come up with, I think Ford was trying that. They licensed it for a few years by spraying copper, just alloying the zinc to make a bronze out of that. And you can get the mechanical properties as good. But anytime you're introducing another process in the manufacturing, they don't like it. Okay? And both of you are from car industry, you know that's Ford licensed it, and at the end they saw the mechanical properties they can get, but it is another step which add to the cost. And with the help of business school, we found out how big is that problem. They found that the scrap cost is about $434 million every year for Detroit. That during that welding, body in white welding, they lose so much more material, plus doing that many more welding. But what we found, when you do the laser welding, each time there is a porosity or breakthrough, any defect, it manifests in the spectra itself. And that's what got us interested. The certification part, it was, our colleagues always argue, I'm doing fundamental, or I'm doing applied work and things like that. And whenever my young colleagues ask me, I said, everything is fundamental if you look hard enough in it. Okay? So that was basically in Aetna Industries, which is now called AG, came up with this problem. We come up with a solution looking at the spectra. Now it has become, and in the next few minutes I'll show you how many ways you can find out the information just looking at the spectra. The shape, the intensity, all kinds. And that was, we already got the patent some time back just to look at the defect in body in white welding. But after that, we come up with many other things. And the question is why this is important. There's an article I found in Forbes. US industry loses something like $57 billion a year on quality issues, okay? Including using the statistical quality control, okay? So that's a major issue, and at that time, our Treasury Secretary said that, this is a big handicap to improve the life of society. So why in-situ? Welding for defect detection. And using that spectral example, what we found that looking at the spectra, I can not only tell you it's a good weld or bad weld, I can find out what is the microstructure, what is the porosity is there. And now we have found, just recently, according to my students 75 days back, we even submitted a paper on how to find out the properties of the material while I'm fabricating them. There's a 3D printing or welding or anything. So we can get, the light is really enlightening in the sense it carries so much information. The composition, the microstructure, the phase transformation, and now the properties. So what we found, we call it smart optical monitoring system. I have to remove this. Just few days back, the patent is awarded, so now we are protected. Right? But that's not only the tool we need to find out. You also, at the same time, had to develop a mathematical model for online use. And that's the problem. The model I described at the beginning, it has all the physics. But what I didn't tell you, it takes about 4 days to converge in the supercomputer. So it's never be used in manufacturing. And if you want to use it for manufacturing, you need it to converge in 2 to 10 milliseconds. Because that's the typical interaction time between laser and the material. So how do I do that? How do I keep the quality of the model and the physics of the model at the same time do it faster? Okay? I asked the same question when the dean of Berkeley was giving a talk this Tuesday. He was basically indicating everything can be solved online. I said, tell me, how do I get it? What computer I use to get such a quick convergence? And didn't get a straight answer, but my suggestion, and I'm trying to get people to fund me to do this, is if I use that, if you look into a solution of any model, go back to 1940s Rosenthal model, the solution has some kind of geometric form, whether it's a straight line or a parabola, hyperbola. Every system has their own way. You can get the equation, but it has got some kind of geometric form. So my suggestion was, why don't we develop the model, get the solution, not take the direct solution, take the nature of the solution, and then calibrate for the experiment you are doing. And that can be, whether it's whatever geometric form, that can be solved in microseconds rather than waiting for a long time. But I haven't managed to convince anybody to pay me to do that. But the point I'm trying to make is we have incorporated all the physics slowly. And with this as an output from the transport model, I can put that from the transport model output as an input to Abacus for mechanics model, and I can get the whole shebang out of that. What's the temperature history, what is the mechanical property, even how much residual stress. Because one of the big things additive manufacturing people are suffering, the residual stress accumulated over the hours of laser treatment you're doing. How do you do? Now, I have another patent how to recover from it, but I don't have the online solution. So one of the things, I think we can calculate all those, but again, we need to measure it. And using this model, I can measure the composition, whichever part of the part I'm making. With dissection, we can get the three-dimensional information of the composition distribution and the phase transformation. Now, how do I get the phase transformation? First, start with the composition. We have chromium iron, nickel iron. This is basically without phase transformation. And we take 3 other systems which has got phase transformation. Collect the light, analyze it, and basically come up with the information, whatever the composition I want to find. We can develop basically calibration curve for the system we know. And using the calibration curve and Hertzberg's equation, we can come up with the composition we need to find. And your question will be, why do I care? I know what alloy I'm using. I know the composition. Why do I need to find out the composition? For 3D printing, you need to find out the composition. Whenever you're using laser, any kind of heat source, which is giving you rapid solidification, you don't follow your conventional phase diagram. You basically get, and these are some of the paper we published a long time back in 1992. We found that whenever you're doing a laser melting or laser deposition, your phase diagram changes because due to the rapid solidification. It's called atom trapping. There are two formulas. One formula was developed by us, another was Mike Aziz from Harvard. So we are always competing whose is better, obviously, but this happens. So if this happens, you have to have a basically online model and find out the composition, what you are getting instead of what you're starting with. It's never the starting composition, it's a different composition. Now, how do I do that? What we found, if you take a ratio of the two primary, whatever the alloy, this is nickel titanium alloy. We tried in 6 different alloys. Whatever the alloy, you take the two primary alloying element, take the ratio, and if you plot the line intensity, and basically what you use is called growth of curve theory. A lot of things we do, we borrow from the physics community and apply it in our engineering. Excuse me. Whenever the microstructure changes, slope changes. Okay? So by looking at the plasma, and this calculation doesn't take more than, excuse me, more than a few milliseconds. By doing that, I immediately can tell you at what percentage my composition will change and what kind of structure we can get. And we tried multiple systems. This is for nickel titanium. This is for nickel aluminum. And nickel aluminum is very important because that's the base house in nickel superalloy. You'll see kitchen sink in the nickel superalloy, but essentially it's a nickel aluminum structure. You're replacing 1 or 2 aluminum atom with some other element. So even all kinds of different alloys, we tried this and we found that you can always slope changes associated with the phase change. Okay? Now another question my colleagues started asking, there's a lot of fluctuation of the emission plasma. Okay? How do I know I'm accurate? 10 milliseconds, it will be probably, intensity will be high, and then after a few milliseconds, intensity is low. How do I know how accurate or stable that calculation? So what we found, when you take the line intensity ratio, it becomes very stable. So instead of looking at individual lines, we are always normalizing line with another more powerful atoms in the line. So with this, we can get basically fluctuating can be basically normalized. One of the examples is using these two lines. We show that it can, and the bottom line is line intensity ratio is independent of the fluctuation. So we found a way to make this online observation more stable. But once you have that, human beings are greedy. And when I was giving talk to different industries, well, all right, and I know you can monitor the strength and monitor the composition, monitor the phase. What is the property? That's why I'm more interested, because I want to still I have to take the material, cut into pieces, make tensile sample, fatigue sample, do all this. So we started looking at, is there any way we can find out the properties of the material online? And essentially, we found a lot of work was done on matrix effect, how the structure affects the plasma. We want to do in situ determination of the mechanical properties. And the easiest thing is to start with the hardness. Hardness have a correlation with the yield strength. So we're doing that. So there's a huge potential. So all right, it's worthwhile to spend time to look at it. And I can basically, if I can model that, I can essentially get what are the particle density of the plasma itself over the melting pool. I can get the energy transfer of the plasma. Putting all those, I have a way to calculate what we should expect. And collecting the emission from plasma, we found that we can, using basically peak profile fitting, by doing this bunch of juggler education, we can find that I can find from the intensity what is the micro hardness of the material we are treating with. Okay? And once I find out the micro hardness, I can find out the tensile strength of the material. So with the plasma, not only we can get what is the composition, whether there is a defect, what is the phase transformation. Now you are beginning to look at the plasma online. In 10 milliseconds, I know what I'm getting. And this was just a small instrument. And this time, thanks to the university, when Ford licensed it, I get a letter before 2013 Christmas or 2014 Christmas. Why don't you start your own company to make this instead of just license it to a company? So we did that, and this is the total instrument. Now we basically reduce the size to half, and already installed in a Chinese company where this month will be installed in an Indian university. So these things are beginning to get tracked. But being a faculty, I'm one of those person not lucky as Alan. I never left school, couldn't get out of it. But I launched a couple of companies. But the thing being academic is basically bothering me to see how come I'm getting the information from the plasma, which is basically driven by quantum mechanics, and predicting something in the solid, which is driven by continuum mechanics. So that's something I even took a sabbatical, spent time with David Webb in Santa Barbara. After 6 months, his parting comment was, Jyoti, I work with one atom at a time. This is a million atoms at a time. It's not mathematically tractable. But I don't give up things that easily, so I'm looking at how I can sort of forward the problem further, fundamentally. But that's the last few slides. I'll show you that this is the work I'm working with Amit. Amit has a huge expertise on how to increase the strength of aluminum by making the face smaller and smaller. So with Amit's help, we are beginning to look at what we can do to improve the properties. And basically, using laser to make the phase, we go down to 10 to 30 nanometer size, and these are the system we found. And the literature shows that the two types of eutectic formed in these alloys can improve the strength. But it's a very conventional process, is very time consuming, and you cannot really make the phases any smaller. So what we started looking at is how we can get the high cooling rate, which is natural with laser, precise control over the cooling rates, engineer the materials with varying phases and features, and ability to tune the mechanical properties using laser treatment. Okay? So this is the aluminum copper system. This is the eutectic we got. But we found that in this system, aluminum copper silicon system, we get two types of eutectic on course. And that was done, this is published in Nature Scientific Report by Song and Wang et al. They used the conventional techniques. We wanted to see whether I can using laser, I can duplicate that. And we found not only we can duplicate that, we can make it finer, and we can get it quite substantially increase in the plastic strain. Okay? So what I wanted to tell you that using laser, essentially the topic was how do I engineer the material with lasers. I want to show from not only I can modify the property, create the structure you want, I can even tell you what structure I'm getting. So not only are doing it, you're also measuring it right at the same time. And I'm at this point negotiating with NIST and DOE to see whether this can be a new type of measurement technique. Because nothing is available at this market to give those information in the in-situ. So with that, I'm in time. This is the summary of, we can engineer the material with desired properties. We can model the process sensor and control optimization. That's what we're trying to implement. And the first time in the world, you'll have a capability to predict the properties while you are making with laser. Thank you.